we're gonna talk about one extra thing today, and then we'll start reviewing. So one of the downsides of having a class that's once a week is that it's hard to review, right? So we're gonna review today, but then a whole week will go by. Okay, so I am going to be here on Tuesday from 2 to 6 in the AEC. If you have any final questions, that's usually when I see a high percentage. It has been fixed. Thank you. So that's when I see a lot of people all of a sudden. But, you know, I'll be there answering whatever questions you have. Today we'll get what those questions are. I'm going to take any questions about anything we've talked about so far, about rotating. Please, sir.
When the homework.
Yeah. Let me get a new one.
I was working in the question 11
Yeah.
and 10.
Please.
And for B,
He's getting on his walking shoes.
I cannot find this calculation for here to here. This is the answer, but I get it wrong. So, well,
Wait, so I'm sorry, they give you this?
yeah, this is the problem.
Yeah.
This is
Okay,
the
that's perfect.
And when you get to answer A, then you jump to B, and the letter
They didn't, okay, that's perfect. And so it's the end. It's what is it? It's cosine x from where to where? It's the cosine of 4x.
4x. And then interval is 0 and 5.
0 to pi.
Yeah.
Okay. You remember this one? Okay.
Then actually use the tecnología to resolve the correct answer.
There's no better way to say it. I just prefer technology in Spanish than tecnología.
Oh.
I love it. I absolutely love it. Okay. Yeah, that's right. And that's one of the points I wanted to make. And here's what I'm going to ask about this is test question number 9, as I have counted in my other class. That may be false for this class. We'll figure that out in about 40 minutes. Okay, maybe a little bit longer than that. But question number 9, at least on their test, is going to be about arc length and finding the length on this curve. We can plot it. We're plotting the cosine of 4x on the interval 0 to pi. So plot my way at the bottom. Plot the cosine of 4x on the interval x equals 0 to pi. Yeah, we're using the arc length formula. But what I'm going to say is write the integral that represents the length. And then I'm going to give you extra points if you can actually solve it.
So it's be like the square root of 1 plus dy dx.
Squared, that's right. That's what we're about to do. Yeah, so yeah, for me it's a giveaway problem. It is an absolute giveaway. Right? So I'm not asking that much. How long is this, right? It's the integral from 0 to pi of the square root of 1 plus f comma of x squared. Right? So I'm going to do one soon in which this one we cannot do by hand. Okay. That's when you have to use the technology. I have to say it right. But the technology, okay. So I know I can't. I just can't. All right. F prime of x here in our sleep, okay. Minus 4, the sine of 4x, okay. The integral from 0 to pi, the square root, 1 plus 16 sine squared 4x dx. And that is the end of the game if we're playing by hand. Okay.
I was trying to solve that one.
No way. And this is good. This is good. I hope you just beat your head against the wall over and over again so that we can see again that there are some integrals that we cannot do by hand. And again, the one that's most important to us is this one. I guess I need to put in here because I don't want to keep it. But it's the integral, again, from minus infinity to infinity of e to the minus x squared over 2. And it's like a 1 over 2 times the square root of pi, right? I barely made it. But that one, that's the one we use in stats. Okay. Yeah, that's the one we use. That's the normal distribution, right? That one we cannot. We have to have a table for that one because we can't find the exact values for that one. Okay. Okay. But this is another one. So how will we approximate this? No, we can't do this by hand. Right. So there's no antiderivative of this.
I mean, integration by parts? I mean,
No. There's no antiderivative that we can write as a regular function. Okay.
Put it in Maple.
Put it in Maple. We're about to put it into Maple. That's right. That's exactly right. And that's what they mean by doing using technology, right? And I think that again, I'm not bashing my colleagues, but a lot of my colleagues are still in the 70s.
But to resolve that problem there, we know go to have that kind of problem in the sound, right?
No.
Because we know how.
So that's what I'm saying. I'm going to ask you to write the integral, and then what I'm going to give, you can do, but it's going to take forever. I'm not going to ask you to do it, but if you do it, I'm going to give you extra points.
When you say forever, how long? Like 30
Well, no way. But in the course of an hour and 45 minutes, which is what you'll have, you should not be spending that much time on that problem unless you absolutely blank on something else. So, cosine 4x? I think I have to put the times here. And then 0, was it pi? Right. So yeah, in an instant.
So what problem is 8.814?
Right here, yeah. Yeah. So the integrand's in red, and then I'm sorry, f is in red. The integrand is the square root of 1 plus f prime squared, right? So that is in blue, right? And now you're trying to find the area under that curve, and that is in green, right? So the length of it, ultimately, of the whole thing is 8.81 something. But as you go along, you get to see what the length is. Okay? Questions about that? Let me give you one that I might give. 6, 5. Something like.
Is there something you can do with the lights to make the board more visible?
Let's see.
Maybe.
Is that okay?
Yeah.
8? Number 8. I guess something like number 8. Again, write the integral that represents the length of this function. I'll grab this one too. I didn't grab this in my other class. See how much I love you all? X to the 3 halves over 3 minus x to the 1 half. X to the 3 halves all over 3. I think that's going to work. Minus x to the 1 half. I think I may have to put absolute values here because Maple has problems with. So yeah, I may just want to get out of this. So plot the absolute value of x to the 3 halves, right? And then that's all over 3, okay? And then minus x to the 1 half. Right. And then x going from 4 to 16. All right, what's the length of that? All right, write an integral that measures the length of that. So in this case, f of x is equal to 1/3 x to the 3/2 minus x to the 1/2. Well, keep in mind that, of course, we know what we're doing. We're trying to use the integral. We're just going to use this formula, right? F prime of x is equal to 1/3 times 3/2 x to the 1/2 minus 1/2 x to the minus 1/2. This is a derivative, not an antiderivative. Simplifying just a bit, 1/2 x to the 1/2 minus 1/2 x to the minus 1/2. We'll need to square that. One-fourth x. Minus what? No, you square it, right? So it's this square. So it's this square, and on the other end is plus 1/4, right? X to the -1. What's in the middle? 0. What's in the middle? So 1/2. Right? So a plus b squared is a squared plus 2ab plus b squared. And so when you square a plus b, and this is just Pascal's triangle, okay? When you square a plus b, then you get a squared plus 2 times this times that plus b squared. So this times this, x to the 1/2 times x to the minus 1/2 is 1, so that's just 1 times 1/2 times 1/2 is 1/4, but then you multiply by 2 and that's 1/2. It's the integral from 4 to 16 of the square root of 1 plus f prime of x squared. If I want to be obscenely deliberate, I'll go ahead and do 1 plus f prime of x squared. I'll remark that that is 1/4 x plus 1/2 plus 1/4 x to the minus 1.
It's minus 1/2, isn't it?
I added 1.
Oh.
It's 1 plus that. That's why I have it in red. Because adding 1 makes it a plus 1. Okay. And so literally, you can just leave it like this. The integral from 4 to 16 of the square root of 1/4 x plus 1/2 plus 1/4 x to the minus 1. So far I see 10 problems on the exam. Okay, so roughly 10 points each. Exactly 10 points each. Right, so this to get you 10 points. But then if you're struggling on the antiderivative of 1 plus 1 over 1 plus x squared, again, I'll say solve this if you can. Finish this off if you can. Now this is one that was given in the exercises, so you would expect Briggs and Cochran to expect you to finish this. So there's some way to do this, okay? So now again, whenever we see an antiderivative at this point, the only thing we know how to do is use substitution, okay? You don't substitute here, you just have to recognize that this is a perfect square, right? So this is, the remark is that this is equal to the integral from 4 to 16 of, this is what square? We got a hint to it. From this, right? This is almost a hint, right? So when we squared this, we got a minus. And so what do we need to square to get a plus, right? So it's 1/2 x to the 1/2. And this is plus 1/2 x to the minus 1/2. But you just need to see that. You need to see that, right? So that's why, we can put this in parentheses, right? But for extra points, if you can make that observation, so be it. And there'll be some other problem that if you see, you know, how to finish the rest of it, more power to you. But if not, that's perfectly fine. Okay. So that now that we've observed this magical observation, then the square root and the square cancel, and then it becomes a simple power rule that at this point we can do in our sleep. And then you finish it off. And again, that should be an absolute value, but everything's positive, so I can drop the absolute value. Okay. Questions about this? So I'm taking this, any of this is the answer. All right, so running through this is equal to, by the fundamental theorem of calculus, 1/2 times, add 1 to that, so that's 2/3, x to the 3/2 plus 1/2 times, add 1 to the power, divide by 2x to the 1/2, evaluated from 4 to 16. I think this actually turns out to be a reasonable number, but this is equal to, that's 1/3 times 16 to the 3/2 plus 16 to the 1/2 minus 1/3 4 to the 3/2 plus 4 to the 1/2. So 64 over 3 plus 4 minus 2, whatever. Questions about arc length?
So with that technique, I can go back and try to resolve them for B.
Say it again? I didn't hear you?
When I go back to my homework,
Yeah.
so I see I use the same technique, then and do it that way, they're going to give me the correct answer, I mean
Yeah.
the answer.
Okay, yeah. Okay. I'll be ready for some concept questions. People who've had me before, know that sometimes I'll throw in some questions like this. I hope it's not that difficult. Maybe I should just give this as extra credit. How much extra credit do we have? 20 points, something like this? That's a ton, isn't it? Are you afraid to say how much it is? So that I might start taking some away? So that any continuous function connecting 0, 0 to 1, 1 has length greater than 1. So I'll give some extra credit for 2 things. So show using the formula, the arc length formula, and then show using some very basic geometry. So any curve that I have connecting 0, 0 to 1, 1 has to be longer than 1. All right. Even or odd? Odd? We'll make that worth 5. We'll make this worth 3, and that's worth 2. So 5 points. I could throw something like this on the test. It would be worth a couple of points. Okay. So ask me about that at the break if you have questions about that. Again, all extra credit due next Tuesday. Questions about arc length? Anything? 0 to 10. 0 being trivial, 10 being impossible.
It was trivial last Tuesday night.
It's harder today?
At this point, not trivial.
What happened? I kept running my mouth? No. Okay. What happened? Did I make it harder?
It's just been a week after.
Oh, it's easy. Oh, see that's also the problem. Yeah, but again, my 30 minutes every day. It's like working out. No. Okay. Yeah. I need you just look at me like, yeah, right. Okay.
We're working at this one.
What'd you say?
So we're working.
Okay, good. Yeah, I hope.
30 minutes to do one of them.
Do one of what?
Of the homework problem.
Like which one?
That one under with the
Number
time
8
equals
from
time.
section 6.1, 6.2, 6.3, I've done it like 6 times, and I still can't get it right.
Right, and I guess we should talk about that. That just shouldn't happen. This is time for you.
It's algebra that I'm getting.
Oh, see,
Not
that's
God,
all the
not
more reason. So yeah, so from a
oh my
and
God,
I,
I cannot get the freaking numbers.
please do not get obsessed with my math lab, with you forcing my math lab to love you. My math lab is not going to love you. It makes for a bad significant other. Okay, so if you want my math lab to tell you good work, it's a bad parent. It's not going to be supportive. If you don't put 1 over 2, you know, if you put 2 over 4, it's not going to like you. Right? So please, just move on. Yeah, yeah. Particularly because I'm giving you full credit on the test for that. So don't, please. Okay. I think we're going to leave this section. We're going to move on. 6.6. Right, so we're doing some physical applications. All right, so we're doing some density and mass. Okay, so mass is density times volume. I never think about it this way. Okay, so I usually think about it as density is mass divided by volume. Right, that's the way that I think about it. That if you want to talk about how dense something is, then you're talking about how much mass it takes up out of all that it is. And in 3 dimensions, all that it is what we call volume. Okay, so it's how much mass per unit of volume. Here we have a bar. Okay, so we have a bar in 1 dimension. It's supposed to be really, really thin. Okay, and the change in color here is supposed to represent a change in density. So let us suppose for the moment that it's more dense the more we move to the right. Now, earlier in the class today, we were trying to think of an object that has that property. Think of an object that is not uniform in density in reality.
Baseball bat.
Say it again?
Baseball bat.
Baseball bat. Was that right? I didn't know that. So what happens to a baseball bat?
Well, because the part that you hold, it's much thinner than the very
Right.
edge of that.
Right.
You have to make it-
Yeah, that ends it. Right. So I can't wait to bring that up to them and make them look silly. That's good. So baseball bat. Okay, so it's more dense here. We want to calculate the complete mass. Okay, of this. So it's dense here, more dense over here. We want the total mass, and as you might expect, or maybe you don't expect, we're going to break up the interval from A to B into pieces. Okay, and on each small piece, we'll make the pieces small enough so that basically on each piece, the density is constant. Right? If the density is constant, then we just have the regular formula that it's density times the volume. That's the mass. Right? And so we break up A to B into small enough pieces so that on each piece is constant, and then we can just calculate the mass on each one and then add everything up. Okay. The conclusion should not be shocking to you that when we do that, when we break up the interval from A to B into pieces, each of length delta x, and then add up the masses, the sum of the masses is the densities times the width of each one, then in general, if we take infinitely many rectangles, that the mass is just the integral of the density. This is the lesson. So suppose the thin bar, or y, is represented by a line segment on the interval A to B. with density function rho with units of mass per length, the mass of the object is simply the integral. Okay. And here's what I want to say. I want to say just in general that you see that the integral is the basis of all calculus. Okay, so I have been harping, particularly in Calc 1, I have been harping on how important the derivative is, and it's really important, but it's the integral that time and again comes up in applications. And the derivative is only important because when we evaluate these integrals, we keep taking antiderivatives, okay? But time and again, we are always wanting to know, what is the total this? What is the total mass? What is the total work done? What is the total this, total that? And my job is done if a decade from now you're reading a paper and one paragraph says we want to calculate the total blah, and the next paragraph they show you an integral and you're not slightly surprised that it's an integral, right? So when someone's trying to calculate the total whatever and an integral shows up, that makes complete sense, right? Calculus continues to come into play when you have objects where things are not constant, where the density varies, where the force varies. Okay, so I mean that's what the integral is about. All right, so that was me on my soapbox. I'll be back on it in a second. Let me take this. I'm going to take this. The final question on the exam. I'll give you a function representing density. You have to tell me the total mass. All right? I'll give you a function representing density. That would at least be part A. All right? But the idea is all the same. Just breaking up the integral into pieces, calculating each piece, adding everything up, and then making the pieces as small as possible. Okay. Questions about this? Typical problem. A thin 2-meter bar represented by the interval 0 to 2 is made of an alloy whose density in units of kilogram per meter is given by 1 plus x squared. What's the mass? That's about as straightforward as it gets. And again, it's an application. That's pretty straightforward. Oh, that's right. We have some engineers in here. There weren't any engineers in my other class. We have some engineers in here. You'll see the integral all the time. All the time. It may be the most used mathematical concept in engineering, along with the derivative, of course. Yeah. No brainer here, right? So the integral from 0 to 2 of 1 plus x squared dx. Absolutely no brainer. I'll take questions about that. Say it again?
14 over 3.
Yes, I think it is 14 over 3. X plus 1/3, x to the third evaluated from 0 to 2, 2 plus 8 over 3, 6 over 3 plus 8 over 3 is 14 over 3. So 2 plus 1/3 times 2 cubed is 2 plus 8 over 3. And you can leave it like that if you want, but 6 over 3 is 2 plus 8 over 3 is indeed 14 over 3. And the units are what? Kilograms. 14 over 3 kilograms. So the only hard part is it all depends on what function I put here, right? The point of this problem is for you just to remember that mass is given by the integral of the density when the density is not constant. Questions about that?
So is that as easy as it looks?
Yeah, it just depends on the function. So if I say the density function is whatever, then it's just about whether you can integrate that function or not. So application problems in terms of difficulty aren't that difficult. because you're still doing the same thing you're doing. It's just a way of interpreting it. I don't think there's anything down here that's like pressing. So in the exercises, we'll see, right? I'm sorry, 29?
No, 9.
Number 9.
Mhm.
What's number 9 say?
26.
The sum is
1 plus the sine of x? That's a problem? Or you want to do it?
Try.
Oh, let's do it. Okay, let's knock it out. The integral from 0 to pi of 1 plus the sine of x. Great. I think you can do this pretty straightforwardly. Do I have too much faith in you? So, yeah, can we even imagine what that is? 1 plus the sine of x, right? So, plot 1 plus the sine of x. Did it give an interval? Thank you. Yeah, thank you. Appreciate that.
Does that mean that the sine graph moves up 1?
Yeah, you just moved the sine graph up 1. It has density like that moving from left to right. So, I don't know.
Density doesn't really change that much.
Say it again?
Density doesn't
I know, it doesn't. And, you know, you have to think of some weird examples,
Like
right?
an airplane.
Airplane.
The wing would be less dense than the.
Yeah,
center of the
something like
wing.
that. Yeah, that's right. Yeah, move from left to right. Yeah, so airplane. I like it. Okay. Yeah, so it's just integrated.
Density, are we talking about density or shape of something?
Oh no, the amount of mass per volume as you move from left to right is given by this value.
I think it's better than water and air.
As you're going from where to where, though? As you're going from, so we're moving in a straight line. So almost, yeah. So we need to mimic this as a straight line. So the airplane example, right? So if you put the airplane down like this, right, and you move from left to right, looking at the density, you know, mass per unit of volume, then unless I guess you're claiming that the wings are heavier, right? As you move from, so the wings are like here, right, and add to the density.
Well, the wings are lighter.
But then why do you have more?
What? Because it starts out a low density, gets higher, and then gets lower again.
Because of the wings.
Right.
Because you've added the wings.
Because the wings are lower density, right?
Right, but you've added more, haven't you? Haven't you add? Oh, but you're talking about the ratio.
Yeah.
Right. So, but then that wouldn't follow this because there's more here in the middle, right?
The density is highest in the middle.
Yeah, I don't know if we're saying the same thing. Yeah, I don't know if we're saying the same thing.
Because
Yeah.
if 1 plus sine x is the function of the density, that means the y-axis represents the density, right?
Yeah, that's right.
So that means in the middle, the density is the greatest.
Yes. But you were saying, but do the wings add to the density or not? That's what I'm asking. Right. So the ratio may not be the same. So the density, so the mass per volume may not be the same because the wings may.
Well, it depends on if the surface area of the wings is significantly greater than the surface area of the center of the plane.
Okay. I can believe that.
It's dependent both of them,
Right.
mass and volume.
Yeah. So yeah, I don't know about that example. So maybe if you had some really crazy candy bar, okay? So where all the stuff is in the middle, right, and then on the ends.
Baseball has a rubber and cord middle.
Oh, so maybe. Okay, so if you lay the baseball down and go from left to right. Okay. That's interesting. Okay. So, but you can do this. What did you get?
I didn't have-
5, 9, negative
5 plus 2.
5 plus 1.
Okay. Now, you're telling me all these sines and cosines of pi, right?
Well, but it's not, we can plug a 0
But you
pi
can.
for A and B, or not.
A is 0, B is pi.
Uh-huh.
Yeah. And this is one of the few exceptions where actually we're like a number here, right? The integral from 0 to pi of 1 plus the sine of x. What's the area? Yeah. Right, so x minus cosine x evaluated from 0 to pi, and it's just the minus sign game, okay? So pi minus the cosine of pi minus 0 minus the cosine of 0, right? So that is pi minus negative 1 minus negative 1, right? And so that is pi plus 2.
Also, I also have to cancel negative cosine divided by 1, right? I just leave it like that, like pi negative cosine pi plus 1. So
Pi negative
yeah, I
cosine
just have it there. So it should be
plus
something-
1. Oh, no.
It should be
No.
something-
You got to tell me that's negative 1.
Okay.
Yeah, you got to, you got to do that. Yeah. The cosine of pi is negative 1.
Cosine pi equals to 0,
Cosine of pi.
Oh, I'm sorry, this is 1. I'm sorry. So they cancel, right?
Right.
So that's 1 minus, yeah, thank you. So pi it is. I apologize. You had a question?
I don't understand why that cancels, and you want us to leave it in terms of pi.
To review the trick.
Oh yeah, that's fine. That's fine. So minus, oh no, I shouldn't have changed that, right? Trying to convince me.
The cosine of 0 is
Yeah, so this is minus 1, yeah. Because this is 1, minus 1, and then a minus in front of it.
That will be 2.
So it's minus this, but that's 1, so it's minus 1.
Well, negative cosine pi is 1 positive.
Yeah, that's right.
And the other one is positive, so it's 2 pi.
It's pi plus 2.
Yeah.
Yeah.
Okay.
Yeah. So, but the point is that none of these things bother us, right? We aren't intimidated by any of these functions, right? There may be some piecewise ones down here, but you would just integrate on each piece, and it's not even that big of a deal. Yeah, and just add them, right? So, none of that is difficult. Okay.
The 13 number pi. Number 13.
Number 13, how do you do 13? Yeah, u is 2 minus x squared, du is minus 2x. You know how to pull out the 1/2 and do all of that stuff, so yeah, this is not. That's why I was saying that the examples are just going to fall into something that you already know how to do. Okay. Yes.
On the exam, like basically we'll go in order, like starting from.
Yeah, we're gonna construct the test in a few minutes.
Serious?
We're gonna go 1 through 10, and we're gonna go through exactly what I'm gonna ask. That's see, I'm telling you.
You should get. I'm gonna vote you for the convocation. See what you get.
Okay. Oh, go ahead. Go ahead. Feel free.
That's what I think math should be, because it shouldn't be tricky or anything.
Well, I mean, I'm not. I got other ways to be tricky. Okay, so I mean that's not that big of a deal. Work is force times distance. We have some engineering people in here. You all know this better than I. This is good. Right. So what the hell is a Newton?
Force required to move 1 kilogram, 1 meter in 1 second.
Okay, so a Newton here at least is the force required to give a 1 kilogram mass an acceleration of 1 meter per second squared. And you know this guy Newton, right? Kind of important. A joule is 1 Newton meter, right? The work done by 1 Newton force over a distance of 1 meter. Okay, so work is force times distance. And so again, when the force changes over time, when it's constant, then you can do the nice physics stuff, right? But when it changes over time, like, can we imagine that? Right, if you're pushing something up a hill, or if you're pulling a bucket of water up, right, with a heavy chain, obviously the work done at the end is not as much because there's less chain to pull up, right? So when the force varies over the interval a to b, then you have to do something different. Well, again, the interval a to b will break into pieces piece is small enough so that on that subinterval the force is constant roughly, and then you add up all of those pieces. Okay, so from that is the obvious conclusion that if the force is represented by F and it's variable from A to B, then the total work done, again, is just the interval from A to B of the force. So again, when you're in your engineering days, you all will have some mechanism to come up with a function that models the force, right? You'll need mathematicians for that, or at least mathematical physicists or numerical analysts. To do that, and then you can integrate to find the total work. And so this is 10B. 10B, I'll give you a problem. You'll be lifting some volume out of some area, out of some space, and I'm going to ask you, what is the total work done using all of calculus? Is there a question? Typical example, let's see here. Let me find typical examples here, right? So, lifting problems, and I'm going to ask a problem like this. So another common work problem arises when motion is vertical and the force is a gravitational force. Okay, so here, suppose a fluid such as water is pumped out of a tank to a height h above the bottom of the tank. How much work is required, assuming the tank is full of water? Okay, so some observations. Water from different levels of the tank is lifted at different vertical distances. Water from the same horizontal plane is lifted the same distance, requires the same amount of work, and the volume of the water is given by rho times V, where rho is 1 gram per centimeter squared. Here's the visual. So it's something like this. I wonder if this is still working. So you're lifting this out. So you have, this is full of water, and you want to pump the water out. Okay?
Wait, is that rooted the water?
That's right. So again, the way that we do this is that we model what we do to one disk of water, right? And see, how do we, what's the volume of that, and what's the work to pull that out, and then we extend that to all of them. Okay. Is it? Is this helpful?
Yeah.
The ebook rules. Again, the ebook it should render me useless, right? So you shouldn't need me. You could just roll through the ebook, and it shouldn't be a problem. I don't think I want this yet. So. Oh, I do want this. Okay, good. So I'll take this. We'll put it here, okay? And so here, what we're going to do, we need to figure out what the force is, and then we can figure out the work. But okay, so we take this object, right? And so we have to imagine what this would be, and in this case, we need to find the area of it, right? So again, the force is going to be equal to the mass times gravity. But the mass is the density times the volume times gravity. The density is constant. The volume is simply the area at that particular y times the width times gravity. And then you can see that it's just that. I should put this. Okay. So this is the volume, that's gravity, and that is the density. And so that's how they get this. It's the area times the width. That will be the volume times the density times gravity. Questions about that so far? And now we need to pull this damn thing out, right? And so now at level y, right, given how far this is, if this is level L, I need to pull it out, right? So this is H, I should say. So we want to pull it all the way out to H, right? And I'm at y right now, then I need to pull this a complete distance, right? So the work is going to be, the work for just this piece is all of this times the distance. And so that's writing down here. So the work is equal to, just for this piece, is equal to rho times gravity times the area times delta y. And I'll put delta y here, it's okay. And then times the distance. Well, the distance is the complete height minus wherever I am. So if I'm at height y and I need to go all the way to height h, if I'm at height y, I need to drag it h minus y. But that's just for that piece. Right? So if I want to do each piece and then add them all up, then obviously you get the integral from a to b of rho g a of y times the distance you need to bring a of y.
Where'd you get that big D one?
Capital D is the distance. Whatever the distance you need to bring y to bring the whole thing out, that is what d of y
So that replaces delta y and h minus
is.
y.
This replaces delta y. H minus y, in this case, is d of y. And so, for the prettier version of that, this.
Like how you broke it down.
What'd you say?
Like how you broke it down to make it,
Oh, you like how I broke it down to make it understandable? Well, you know, sometimes I like to do my job. I just, you know. Other days I just like to be, you know, fucking confusing. I love it. Yeah, but today I just want to be understandable. I've decided. What in the world are my colleagues doing in other class? I just don't understand. You act like they're just doing it on purpose, trying to fuck with you.
Either that or he's like found it because of the testing.
Yeah, I know. He could just be, you know, sucking up to me. It's okay. Here it is here. Okay, so, and again, I'll reiterate that rho, density, g, gravity. I'm sorry, I'm breaking this down too much.
No, that's okay.
Okay, that's the area. That's the distance you need to break it, and that is what happens to the width of the thing you have in common, the width of the piece that you've chosen. All right, so again, density, that's given. This is the density, that's given.
Are they using p so that you don't get confused with like dy?
Wait, this row here?
Yeah.
Rho is just the density of the medium you're in. So if you're in water, the density of the thing you have matters in terms of the mass, right? Because mass is density times volume, right? So you need to know. So that's just a constant.
So I meant the variable they chose.
Oh, it's just. Oh, you mean y?
It's like
You mean?
Just know what row is. Row is the name of the
That's not p.
No, it's rho.
P.
That's rho.
P is
I'm sorry.
So like P is wrong?
No, P is.
I don't know. Where is P written? There's only a rho.
It looks like.
Yeah, it looks like a P, but it's rho. It's rho. So here's rho. Okay, so that's rho. Okay. And that usually represents density. Is that true in physics? They use rho for density. Okay. So yeah, we're big on Greek letters and mathematics. Okay. I used to be the advisor for a fraternity at my old school, and you know, they would just know the Greek alphabet back and forth. We're almost like that in mathematics, where we just have to know the Greek alphabet. Gravity. The area of the slice that you've taken, the distance you need to, so this is the area of the section and that you've chosen, and this is the distance you still need to pull the section to get out of where you're trying to get out of. So distance I needed to pull the section, right? So distance needed to pull the section out. And then finally, this is the width of your section. I'll take questions about that. Yes?
So density is given, gravity is a constant, and you're going to be given the two functions?
No, you won't be given the two functions. You'll be given a situation. And yeah, so we're going to do a typical situation. But yeah, so it's all going to depend on the situation. So sometimes you'll be pulling stuff out of a cylinder, sometimes you'll be pulling stuff out of a cone. And those are the two examples we'll be talking about at this moment. But I'll take any question about understanding this formula.
You just straight multiplying them across, right?
Yeah, you're just multiplying them across, that's right. Yeah, and again, these two are constants. I won't even make any comments about those. I'm just going to pull those out of the integral immediately and just deal with the things that depend on y. All right, so here's the easy one, right? The easy one is how much work is needed to pump all the water out of a cylindrical tank with a height of 10 meters and a radius of 5 meters. The water is pumped in an outflow pipe 15 meters above the bottom of the tank. Okay. Almost. That's almost right. So, let's look at the picture here. So we got something like this. Okay. So we got some cylinder. Something like this. Okay. So. I'm trying, I am. All right, and so water all the way, right? So it's water all in here, okay? The radius is what?
5.
Radius is 5, okay.
And the height is 15. Yeah.
And the height 15. And what are the units?
Meters.
The meters? Okay. Okay. And so now we're going to put an axis here. I wish I could put it in a different color. But we'll put let's put the axis here. No, that doesn't work. Something like this. We'll put the axis here, okay. And so now we need to pick a y. Okay, so we need to pick a y somewhere. We'll pick it here. Pick a different color. We'll pick a y here. All right, now we need the integral from somewhere to somewhere. Rho g, the area at that particular y, and the distance, we need to pick it. It's a cylinder, so that now when I slice this way, right, when I slice it like this, what object is it? When I slice through it and then look at it, it's a circle for sure. The radius is 5, and the area of that circle is pi times 5 squared indeed. And so A of y is a very straightforward pi times 5 squared. Right? So that doesn't depend on y at all.
So you're slicing y.
So you're slicing it this way, right? So you're slicing it this way. It is a cylinder. No, that was given. That's yeah, that's right. It's a smaller one. That's right. We're calculating that volume for that little piece, and then we're going to add them all up. But now that we've done this piece, now we just need to figure out how far we need to take this out. Right. So they were saying here, we're going to move this all the way out, a distance of what? So where's the? So here, so. And a radius of 5, the water is pumped to an outflow pipe 15 meters above the bottom of the tank.
Yeah, the height of the tank.
The height of 10, right, and a radius of 5, but the water is pumped to an outflow pipe 15 meters above the bottom of the tank.
So the height that you put in there, you have 15 meters, so you're doing the whole bottom of the tank too.
Oh, let's see. So you're saying, where are we? Oh, so this is only 10.
Right.
Oh, okay, very good. So, here. This is 10. So there's another 5 meters here, okay? Right. Oh, here? It's cute. Yeah. So let's see if we can go here. That may bother some people. I had some people in my class in the past who I guess weren't used to people having crazy hair. And so I would come into class and I had one student who would say, could you just have a hair out of place? Could you just, and I was, you mean this one? And they're like, yeah. And I was like, oh, okay. Yeah. So, you know, get used to it. And then she would also, like, I would have like a pocket out and she'd like, could you just put your pocket in? And, you know, it's just crazy, yeah. So, so I'm sure that thing was bothering somebody, so. That's right.
No, I was saying that they had perfect height.
Oh, did it? Okay, so you were happy with it, and I got rid of it. I'm sorry. The integral. From where to where? 0 to 15 of. So 25 pi, right? And then how far do we pull this? 15 minus 1. So I have some serious problems with one of these 15s, right? One of these 15s I don't like. Which one? This one. I don't like this one. Why? Why don't I like this one? What does this imply if I put a 15 here? Yeah, that's right. That I picked a y at level 15, or that I picked a y specifically at level 11. I don't pick a y there, do I?
Why does it imply that?
Only because y varies from 0 to 15. That's what we're implying, right? So these numbers here implies that that's the range, that's the interval that y belongs. But there is no y corresponding to 11, right? It is 0 to 10. Is that okay? So I took a y from here to here, not at 11, not at 12, 13, 11.5. Okay? So it's the integral from 0 to 10. I don't take any questions on that assignment for y. Right? So pick a y in here, not in between here. Okay? And again, in our study, you can do that one. Okay.
X through that Y.
Say it again? Oh, that would be fantastic. How can we do that in a nice way? I got some tools up here, don't I? No. Right. Not here. Right, so why is here not there? Do we need to do this?
So you pulled the roll and the gravity?
Yeah, they're constants, and so whatever the constants are, that's we're in meters, is that right?
Yeah.
9.8 for meters, right? And then 1 kilogram per whatever. Okay.
Yeah, but you pulled the 25 pi out.
Oh, absolutely.
Constant.
Yeah, that's right. So that's 25 pi rho g, and now.
Were you giving the roll and gravity?
I'm sure that you are. I'm going to give them to you, but I don't really care about them in terms of they're just constants, and I'm a mathematician, and we just call all constants capital C. So.
C for everything.
Yeah, that's right. That's right.
You'd ask before you knew what happened.
Okay, so yeah, so 15y minus 1/2 y squared, 100. I think it's 100. Did you get 100? I know you worked, my man. Can always count on you, right? So this is 2,500 pi rho g, whatever those constants are. Okay? Questions about this? Ready up to level? All right, so let's go to some of the exercises. Let's do this one. Emptying this tank here. Okay, so we'll do that. And then I'm going to take this one too. Okay, so so a water tank is shaped like an inverted cone with height 6 meters and base radius 1.5. See the figure. If the tank is full, how much work is required to pump the water to the level of the top of the tank and out of the tank? So just right to the top and out. How much work is done? So again, we'll create an axis. We'll put it right here. Okay. That's about as good as it gets with me, okay? And then we'll pick a y, where we want it to be. And of course, when we slice here, it's going to look like a circle for sure. But now the circle changes as you move up, right? So we'll cut there. And so we need, again, the integral from a to b, rho g, a of y, and the distance we need to pull it. Right, so it is pi r squared in d, pi r squared. What's the radius at the y level? In terms, it's going to depend on y, right? So it's pi times something involving y. I think it's 6 minus y. Well, that's certainly the distance we need to pull out. Yeah, but what is the area here, depending on y? It's a little tricky. Right?
1.5.
Right, that's precisely what we're going to do. Right, we're going to make a ratio, right? So you need to know this distance given this height, right? So we'll get a better picture here. So if I do this, right? So I need to move this. Okay. Ha ha! I moved the dot. That's funny. Yeah, oh yeah, you should see me around my daughter for sure. So here, y is here, right? And so the axis goes through, I don't think I'm going to be that good. No way. So something like that. And so now we want to know this distance. What is this distance here at the y level? Well, I know this is y, so we know that this triangle and this triangle, no, these triangles are related. They're similar for sure. Okay, so the thing I'm looking for here is r, and I know that, and this is y, this distance is y, so I know that y over r, I know, you've grown. Y over r is 6 over 1.5 for sure, which is 4, that's right. So y equals 4r, and r is y over 4. So that's what I mean by it depends on the object I give you, right? If I give you a cone, then you got to do something like that. Maybe use it in a different way, what the radius should be. Right? It all depends on the object. So in the book, what's fair here? So in the book, I think they only give you, like, there's a cylinder.
So the area would be pi y over 4 squared?
Yes, that's right. That's the area. That's right. I'll write it in just a second. Right, so there's a cone. There's a swimming pool that's got some things going on there. There's a sphere. Okay. So.
We're going to need to know all the formulas for area and stuff, right?
Can we know just the basics? Not all that.
You'll need to know a circle.
All right, that's good.
Yeah. You'll need to. But anything else that's ridiculous, I'll probably get to.
Oh, it's in a circle?
Yeah.
Okay.
Yeah. So you won't need to know the volume of the cone or anything like this. Yeah.
I used to go. Oh,
Yeah, we all used to, right? Yeah.
Yeah.
Right, so.
Every day for 5 days a week.
Okay, so then the integral becomes. So this is now y over 4. The integral from, we're taking it from where to where? 0 to 6? 0 to 6 of pi times y over 4 squared. How far do I need to bring it out? If I'm at y level, how much is left? Take it out. 6 minus y indeed. 6 minus y dy. There's some constants in front, right? Rho, g. And there you go. I'll take questions. So yes.
So, this might not come out right, but so when you lift it to like the previous one was 15 meters, does all the water, like if you can seize all of it and lift it to that exact height, all of it's on the same height? Or
Yeah,
does
all of it's on the same height.
Or do you seize it all at once and lift it straight up?
Seize all of what? So we're just seizing discs. We're seizing a disc of water.
And see how much work it would be for this disc
To go, that's exactly right. Yeah, that's right. And so each one, so this right here for each y, this represents along times rho times g represents the work done for one y, and we need to do it for every y, and every y goes from 0 to 6. So we sum up all of the work, right? I should say we sum up all of the forces, you know, from 0 to 6.
But there's really no way to get that to happen.
No, that's right. Yeah, that's right.
Unless
So
you
it's a
have
way of modeling it.
right at the very surface.
Right. Right, yeah, yeah. You can't literally take a disc every single time, yeah. But can we make the argument that it's the same work?
Well, because it would have a different amount of displacement if, like, you used a straw to, like, get it to that height, but you took all the water from the bottom. Would it work? Okay, conservation would work.
I was going to ask. You would know better than me. I was about to say, I think that it doesn't matter how you formulate, how you're taking the water out. The work should still be the
But
same.
I'm saying when you
Yeah.
lifted to 15, all the water just doesn't pool at right at 15. It would.
Right, yeah, that's right. It has to, that's right. That's right.
So you may as well just take it.
May as well do what? Just take the, yeah. But if literally, okay, so the question is not about how you're doing it. The question is, what is the work done, right? And if I say to you that it doesn't matter how you take it, the work is the same, then there's no problem in using the disc way of evaluating how much work it is. Right? So it's not saying you should take the water in discs. It's saying that if you want to find out how much work is done, the easiest way is to look at it in terms of discs. All right, questions about this. 0 to 10.
I mean, I give it like a 7.5.
7.5. I think this is going to be one of the harder ones, okay? So it's the last one. I'm going to put some problems up on my math lab to give you some practice. It's not my intention to give you something ridiculous, okay? So I think it's going to be a cone or a cylinder, and That's it, unless I get, you know, super creative. But I've not been creative. I have to have sleep to be creative.
It's funny how they
Okay.
give you like 35 steps to do a problem like that.
Yeah, well, sometimes it takes it. All right, let's now, should we break now and then review for the test?
We can do that.
What time is it? 45. Yeah, let's break now, and then we'll review for the exam. We'll come back at 8:55, something like that.
We'll come back.
7:55. 7:55.
That is one heck of a
That's
break.
right.
You are
7:55.
super generous.
I think the calculus one problems that we did were way harder. Like,
Yeah.
we had like, you probably know which ones I'm talking about, the classic calculus problem.
Yeah.
The water is coming out of the cone or something.
Yeah, I know. They don't have any where you have the bucket and you're pulling it up and there's a hole in it and the water's coming out. They don't have any. If you look at the exercises, there's not one bucket
She
problem.
loves those problems.
Yeah, I just couldn't believe. Like I was like, I'm definitely gonna do one of these problems,
They
but
were
there wasn't.
tricky because you actually have to think about how you're doing it. Like you have to take the derivative of the stuff.
Right, that's right. You have to find the rate at which the water is coming out, and
And then
yeah.
putting them into the equation and then taking the antiderivative and then you get the answer.
Yeah.
It was,
Those are
then
fun
we did
problems.
ones with speed and airplanes going at the bearings and stuff.
Yeah, the related rates. Yeah.
those were-
Yeah.
Do you know a good website that I can review? The only thing that I'm worried about is like the power, the algebra stuff, like the power rules. And
Well, you
stuff.
can go to Khan Academy. So khanacademy.org. .org, not .com.
That's a really cool website.
Yeah, I like it. He talks about a lot of different stuff. Now, I haven't had a chance to really delve into it, but it's not just him, is it? He has like other people do it. Everything. That's what I figured.
And he's down there. It says everything from organic chemistry to
Like econ.
finance.
Right, exactly. Yeah.
Some of that stuff blew my mind.
Yeah.
The finance stuff is.
I need to take a look at that because it's interesting. Well, that's what I'm saying. That I mean, the model for education we have right now should be getting extinct because so much stuff is for free now. Like you go to iTunes U, you can see
The stuff that you did
anybody.
earlier though, like I bought the book first when I started reading and I was like, okay, it's nice. But then when I started looking into like the harder stuff that we're doing now, like the examples just don't make sense. Like all those letters and stuff that they use, they could be anything. You know, you could get confused. With
Yeah, books are written so badly these days, right? Because I mean, mathematicians write them, and you know, we're just so committed to having a book that is flawless in a mathematical way. Whether it can be understood, who cares, right? It doesn't matter that it can be understood, right? So.
There's no way I can teach this myself.
Well, yes, and I was trying to explain this to some colleagues of mine, but I think the real problem is that we have really paid the price for being wrong in the past, mathematicians, right? Because there have been times in which there have been theorems that we thought were right, and we weren't rigorous enough, and we spent years thinking they were right, and they were wrong, because we weren't like, okay, is that right, is that right, is that right? And so what happens is that because of that, there's a complete like opposite, that you can't write anything without it being perfect. You can't state anything.
Geometry.
Even though if you state it this way, even though it may not be perfect, everyone's going to understand it. You know, you still can't do it because it's not exactly right, right? So, yeah.
I tried doing that last semester, it didn't work out. Like, if I'm stuck in the homework, like those problems in my math lab, there is no way you can figure it out.
Yeah.
Unless you look at YouTube or something.
Right.
There's no way you can figure it out yourself.
Yeah.
The examples, they just jump steps and just do it like their own way. Like,
Right.
You don't know where it's coming from.
Yeah. No, I understand. Yeah.
Trying to figure out what the formula is and how you get to that formula is just.
Well, I rarely skip steps, and I guess it's just from teaching all these Math 99 classes. Like you can't skip any steps with them. So, and then I found that there isn't a lot of extra effort in writing an extra step. Like it costs you nothing.
And
I can
it
understand
actually
maybe
makes more
like.
sense. It saves you mistakes though.
I agree. Yeah. So yeah.
the foils and stuff when you foil.
Right, yeah.
I've done it for so long, you know, since high school and stuff, middle school. So like I skipped those steps when you just learn the way it is. You just do it like when you have the H's in, you know how it is.
Right.
X and H and all that.
Yeah.
You just know where you put the squares and stuff.
Right.
Some people take like the whole page to do it though, but that's fine as long as you.
Yeah, get it right.
Yeah. And then some problems I do it right, set it up correctly, and then I do the computation wrong, and I think I did the whole problem wrong. Just go back and just do the whole thing, and then in the end, I find out it was just like one little sign.
That's all it takes. Yeah, I did not an internship, a summer program at Carnegie Mellon University, where I ended up going for graduate school, and I was doing a project with someone, and on continuum mechanics, and he would have me go off and do this research. So I would go off and I would do all these calculations, like for hours, and I would come back and he would say, "You missed the minus sign here," and I would go back and do all the calculations again for another few hours, and he was like, "No, well, you missed this minus sign right here." And at that, I mean, it was just like, it was like training. Like, I really miss minus signs now. So, when I really don't want to.
I was reading some stuff for my programming classes, and I read what you were talking about earlier, how everything was backwards. You said I read that a Polish guy invented like counting and stuff.
Yeah.
The backward thing. Where you
The reverse polar notation.
Yeah.
Oh yeah.
They said that that's how we should have been doing math.
That might be right. That might be right.
I was trying to understand it, but
I'm trying to remember. I don't remember it that well. I remember like HP was like committed to doing reverse polar.
yeah.
Yeah, that's right. Yeah. Oh, really? Yeah, I know. Was it HP?
Yeah,
I think it was HP that was. Yeah.
Yeah, what?
Hewlett Packard. Yeah.
It's handy for like accounting.
Is it okay?
Because you can do series of numbers like easier. I don't know.
Okay. Yeah, I don't remember. It was like
the numbers
middle
and the
school
sign,
for me.
Yeah, numbers and then the plus and the minuses. And
Right. You put the operation after the
Yeah,
numbers or
after
something like this.
numbers,
Yeah.
yeah.
I remember trying it and it was just so foreign. Yeah, it's just so comfortable.
But in graduate school, you have to prove every one of those problems that you just did. You have to prove, right?
Absolutely. Oh yeah, absolutely. I mean, you know, we have to prove. I mean, you have to prove the fundamental theorem of calculus. I didn't prove that. I just stated it, right? So.
Probably take you the whole class.
Please go ahead.
to prove it.
That doesn't take that long. No, go ahead.
When you talked about showing, what is it, extra credit, what's today?
Yeah.
You said show the basic geometry.
Yeah.
Like, what you mean,
I
like?
think it was slide 3 maybe or 4.
Thank you, sir. I appreciate it. Oh, was it earlier?
Yeah.
Yeah, that one. Yeah.
All right, so we're connecting the points 0, 0 to 1, 1.
I'm just trying to find a link we can use.
Here's the origin 0, 0. Here's the point 1, 1.
This is one? No.
I just want you to show that.
That's the only thing I can think of.
Well, I'm not going to say that much. So you can show it obviously using basic geometry, and then you can show it just using the formula that any curve that's continuous. So you take any function f, and you just look at the Archman formula. For sure, you can demonstrate.
And that's what they use for the distance formula for.
They do use the distance formula in order to create the Archman formula.
Yeah.
That's true. But you can plug this function right into the function. Actually, it has to be smooth too. But you can plug the function right into the arc length formula.
Yeah.
And do a few things and show that that length, no matter what, is bigger than 1.
What
At
if it's
least.
a straight line?
Say it again.
If it's a straight line, it would be.
No, it wouldn't if it's a straight line.
Because it's slant.
So if it's a straight line, it's something else. But
This is derivative too, right?
It's something like that, yeah. So. But that helps with B. That certainly helps with B. So you're doing this again. I'm not answering anything else you have to say about extra credit. Because you just keep weaseling it out of me.
Are you saying his answer solves for B or
Both of them are reasonable responses for why it's true by geometry, right? So there's a theorem about, it may be an axiom. I think it's an axiom from Euclid that says about the distance between 2 points. So.
Can we just accept it as a fact of life, the shortest distance between two points?
I have no comment about that. So I mean, if you say that to me, what I mean, literally a few days from now, if you said that to me, what do you think I would say? Do you think I would say no to that? Okay, okay. Well, yeah. Well, I guess we need to spend a little bit more time together. So. All right.
All you have to do is prove that it's longer than 1. That's how you do it.
All right.
You get it?
Yeah, I mean, it's just a conceptual.
I think number one, we're defining the integral. Now, someone was texting me about the integral, whether they could find the definition in the notes. Was anybody in this class? That's not the definition. So define the integral.
It's all in our notes. I know we get it.
And then what was after that? Some endpoint method stuff, right? Endpoint. Right endpoint and left endpoint method.
The LRAM and the RRAM. I'm still confused in the part where you multiply. I always get confused with the width. Is it on the outside or the inside? What's the constant that you multiply everything by?
It's delta x. That's the width.
That's the width, right?
Yeah.
Okay. I was getting confused for that.
And then what was after this?
The calculus.
Okay, so state the fundamental theorem of calculus. Okay. Then say it again. So basic antiderivatives. And then, is it the chain rule? I mean, substitution rule?
Yeah.
But you actually have been here. You know, I mean, so. And then after that?
It got harder. It got harder.
Oh, that's right. Position and velocity. And so those are initial value problems. Okay, so initial value problems. I'm feeling good. I'm feeling good about this first test. Am I the only one?
I feel better.
Oh yeah, I think it can be done. 7?
It was talking about the areas under the curve.
Area between curves.
Yeah.
And the next one, I think, is the disk.
Right, so, and then volumes, disk, and washer.
And then the shell and spherical. Okay, is there a difference between the spherical and the disk?
So there's a disk washer Cylindrical.
Yeah, cylindrical and shell, they're the same.
So yeah, so disc and shell. Yeah, yeah, right.
Okay, because the book was using shell, and I was like, I thought that was cylindrical.
Okay, and then
Linear.
We did the arc length?
oh, the arc length, right?
And then it's physical applications.
Right, and then it's work and mass.
So 10,
Yeah. I'll take any questions about any of these. Let's see here. So, I don't know. I'm sorry. You want me to put that back up?
yes.
What did you say? Yes.
Volume, this show, I would love to go over
Yeah.
a little bit on.
Okay, that's okay. Good. That's good. I was going to go one by one, but if
That's fine too.
Okay.
But really like focus
But
on number 8.
I have that's perfectly fine, and that's what the previous class said. The only problem, of course, is that if all the other stuff takes time, we may just be too tired. Remember, you're in the clock, so when you just tune out and are gone, so we may have to do this first.
Take the harder part.
I thought I started with this today. Didn't I ask whether we should do any more of these?
We could go in reverse and then.
Yeah, we could go in reverse. Yeah, but now we've already, so that's good. We actually have gone in reverse, so. So that's good. We've done these two already, so let's just go back. Okay.
I like the way you think.
Yeah, the arc length is the simplest one, right? Because it's just the formula.
Right, it's just a formula, that's right. So volumes, let's go back. I think I have that one open. So it was my intention to go over it. 6.5. Oh, and I promised it to my other class, so I'll promise it to you, okay? So 6.5. No, it's 6.4. It's 6.4.
I'm confused about like the y and the x when you.
Well, that's good, because that's what I'll be asking. 27 to 32.
We're doing all that today?
No, I'm asking, I'm using these functions on the test. These exactly. 27 through 32.
So what
This is 6.5?
It's in the
Or is it
book,
6.4?
right?
6.4. 6.4, 27 through 32. I'm going to use these. I'm going to give you the picture. It's some of these. I'm going to have you be rotating these around something. Okay? There you go. Okay. So these are ones where you can do both. Okay? So I'm going to go, I haven't done these yet, but I'm going to go through these and I'm going to figure out which ones you can do both. And then I'm probably going to get those. Okay? Questions about that? Well, let's do some other ones. But that will be the source of the question. All right, so let's move on. Okay, so
If we're gonna use them on the test, we might as well just go with this.
see, give an inch. Take a mile. Take a whole mile. Which, no, I understand. I understand.
So we're revolving around the x-axis?
Around the x-axis, that's right.
Integral is from 0 to 4.
Wait 1 second. Let me get it here first. Speed demon.
So for the x, when you use the y coordinate,
Top and the bottom down.
use the y coordinate system for the x.
All right. So, how are we going to do this one?
Yeah.
I'm going to ask you. Shell method. Shell method.
We're doing the shell. Okay, so the area.
Let's go ahead and give this a heading and everything. Okay, so we have this labeled as question number 8. Question number 8 on the test, okay? So, shell method. It seems like you can do a disk method here, right? Seems like it.
Yeah, you can do both.
Yeah, so let's go ahead and do both. Okay, so, well, let's do the shell method first. If that's true, what are we talking about? We're talking about, whew, talking about this. Rotating that over the x-axis, that rectangle. Right? What function are we talking about?
What do you mean function?
What function?
4 minus y squared.
4 minus y squared?
I thought the function was the top. I mean,
What is it? It's over the x-axis, right? So it's, first of all, you have to write everything x equals y squared, right? Did we do this one before?
I think so.
I feel like we did it before, right? So x equals y squared, and you're rotating around the x-axis, but it's this distance, right? So it's, in general, it's 2 pi y times f of y. In this case, it's f of y minus g of y. It's 2 pi r. It's 2 pi r f, right? So again, when you rotate this around, the radius is just y, right? The radius is y, and the height is this distance. But this distance is 4 minus y squared. 2 pi y times 4 minus y squared. The integral from where to where? 0 to 2.
I'm going to say y, and y.
Y?
Is it 0 to 2?
Y varies. Y goes from the x-axis, y equals 0, to whatever this height is. But at 4, the square root of 4 is 2. When x is 4, y is 2. Yeah. Go ahead. Other questions? Say it again? Yeah, I know. I'm not going to say another word. So, yeah, good. That's good.
I was thinking in terms of 0 to 4 on the x.
Right, and we'll do that. We'll do it that way in just a second.
Oh.
Yeah, we'll do it that way.
Oh, am I confusing shell with this?
Which way is this?
This is this.
This is the shell. If you rotate this rectangle around the x-axis, it looks like a cylindrical shell.
The disk is the one where it goes down.
If you disk, you rotate on the y-axis.
No, 'cause
That's right. If you were rotating that around the y-axis, we would call that a washer, but a disc with a hole in it. That's right.
Because we did disks over the x-axis too. I think we did mostly the.
Oh, yeah, of course.
That's
Yeah,
right.
and I would recommend that if you were given the disk method, if I say do this any way you want, then I would say do the disk method. Right? If we did the disk method, what would happen here? Oh, do we need to go through this? Thank you. This is equal to 2 pi times the integral from 0 to 2 of 4y minus y cubed, right, dy. I do feel like we did this before. 2 pi times y squared minus 1/4 y to the 4th. Did we do this both ways last time too? Or just one way? 2 pi times... Thank you. I thought I said that. Eight minus Yeah, we did do this, minus 0. 8 pi. And we did it the other way and also got 8 pi. So if I hadn't beaten this one to death, then this is something I would have definitely given. Questions about that?
Can you use the formula for that one?
So it's two. So thank you. It's in general the integral, depending upon which variable you're using. It's the integral from a to b or c to d of 2 pi x f of x. That's between a function and an axis. But if it's between two functions, then you have to take the difference as f of x minus g of x. And so for this one, it was f of y minus g of y using the rightmost function minus the leftmost function. Because you're writing it in terms of x, and x is bigger the more you go to the right. And then I think this is still being copied, right? So let's see, then beautiful. And so then finally, the disk method on this. Rectangle's a little different. So then it's this thing, right? You're rotating that around the axis, and that's clearly a disk. And so it's just pi r squared. And so in general, this is right between the axis, so it's the integral from x is going from 0 to 4 of pi times the square root of x squared dx. And that also is 8 pi. So you rotate this around, it looks like a disk, but again the area of that disk is pi r squared times the width of it, and that's the whole volume, and you need to add up all that volume. I'm sorry, you need to sum that volume from 0 to 4. Okay. And then it's pi times 1/2 x squared from 0 to 4, plug in 4, 0, 16 over 2, 8 pi. Okay. So I really like that one.
So the shell method you use 2 pi x f of x.
Yes.
And the disk method you use pi r.
Yeah, that's right. So all of these things are just about what axis are we going around and what method am I asking you to use, right? And so again, we had the diagram. Look in the previous. They should be up here. Look in the previous PDFs. And they should be actually here. And so here's the diagram again. I can copy it again. They call it's under restoring order. And what that means, of course, is which one do you use when. And so I can copy and paste this again. But if you're doing integration with respect to x, if you're dealing with functions with respect to x, I usually don't explain it this way, so I'll explain it both ways. But if you're integrating with respect to x, and you want to use the disk method, then you're going around the x-axis, right? If you're using functions with respect to x and you're going around the y-axis, it's the shell method. Right? Functions of y around the y-axis is the disk method, and functions of y around the x-axis is the shell method. So again, off the record, if the variable in which the functions depend upon is the opposite of the axis, then you use the shell method.
You say that you're always going to show us the picture?
Yeah, I'm showing you the picture. Yeah, it's just being real, right? Everyone can get a picture, so I should give you the picture. Okay. Do you want me to copy and paste this again? Okay. Fantastic.
Can you go back?
Yes, absolutely. Thank you.
And go back up to shell. Wait, the blue is the disk method?
That's right. And thank you, because that makes it better. So this is the disk method. No, I'm sorry. I should put that in green. So this is the disk method here. So this is the disk method. And so the shell, so this has got to go. That's just bad design. My wife would not be happy with me. The integral from 0 to, what was it? 2, thank you. 2 pi. What'd you say?
Can you go back up?
Yeah.
I'm not sure I get where 4 minus y squared equals.
Right, and that's a crucial question, right? So you want to find this area, right? We're moving from left to right. So the function, so this is almost like the area between two functions, but we're moving from left to right. So it's this function, right? And it's just, if we only had x equals y squared, then we're talking about this, right? All the way to the right, right? But we stop here. The other function is x equals 4. This is the vertical line, x equals 4. Right. So I want to know, I'm rotating the area between x equals 4 and the graph x equals y squared. Okay, so I need to take the rightmost function first, x equals 4 minus x equals y squared. Light bulb. I can teach for another 3 years now. Every light bulb has me going a little bit longer.
2 pi x f of x would be for if you're using the shell method around the y.
I thought it was with respect to x-axis.
Yes, that's right. That's right. Yes.
So what you wrote down is like that in green right there.
Yeah, so
Oh, that's just in that. Yeah, that's just in general, but it's up here.
Yeah.
Yeah.
Okay.
Yeah, I can change this to y. That's not a problem. All right. Please, anything else about? Yeah, that too. Thank you.
dy over dx means the derivative
Of y with respect to x. That's right. I have it on tape, but there are no more questions about this. Right now, again, on Tuesday, from 2 to 6, I'll be in there. Open hours. No, there won't be a flock of people. There will not be a flock of people there. No. People are going to be ready to go. All right, area between two curves, number 7. And we can come back to 8, okay? We can come back around to it. We should probably be ending early today, so we should be able to get through this stuff. And if you still have questions about 8, we can go over it. Number 7. There's nothing I can do. I can't do anything with 7. I'm going to give you 2 functions that say find the area in between. Now, I may get a little sick and twisted, okay, and have them intersect more than once, but I doubt it, right? So if I say something like, let me give you the picture for this too, okay? I don't think, I'm not even going to do that. So if I say plot, if I say e to the, x squared, let's see what happens. X squared and x squared, and then the exponential, e to the x. And then I say on the interval x equals, 0 to, let's say 0 to 1. Who cares? Yeah, I want you to find that area.
you use the washer method, right?
I'm going to find the area between the two curves. The washer method gives us a volume. And I'm asking for area.
Integral minus the other.
Yeah, you just take the integral of one minus the other.
So the integral from 0 to 1 of x squared was
Which one's higher here? Which one crushes the other one?
e to the x.
Right, so it's e to the x minus x squared. Right, so maybe I won't label them, so I have something to be furious about. Okay, when you think x squared is larger. But e to the x crushes the exponential. Again, e to the x, e is bigger than 2, okay? So 2 to the x, 2 to the x is 1,000 at 10, right? And x squared is only 100 at 10, right? And they never intersect. Of course, you can prove by L'Hopital's rule that that's the case. Okay, but clearly the derivative of e to the x is much, much bigger than the derivative of x squared. That means one is increasing much faster than the other, and so they will never meet. Okay, I'm done with that. Okay, so they'll never meet on the positive x-axis. Yeah, so this is just integrating. Right, so again, I don't see any problems with this. Just get it right. What is that area? Right, so again, the only problem would be if somehow I had them intersect and you have to find where they intersect. Not a big deal, I hope. And so in green, f of x equal to e to the x, g of x squared, and again, that area there. The integral from 0 to 1, e to the x minus x squared. The functions will be a little bit more complicated, but there'll be things that you know how to do. It's just that simple. So the whole test, it's true. The whole test is just about taking integrals, all right? And so, again, by the fundamental theorem of calculus, e to the x minus 1/3 x to the third, evaluated from 0 to 1, e minus 1/3 minus 1, e minus 4/3. Are we good there? Let's see, I can't get tricky there, okay? 6. Right, so now I have a function, so f prime of x is equal to, suppose I told you f prime of x is equal to, give me a function here, let's say x to the 4th plus the cosine of x. And let's use that. And then I told you that f of 0 is equal to 12. Solve that initial value problem.
We could use two different formulas.
Yeah, you can do whatever you want, right? So usually I just find the antiderivative, right?
Take the antiderivative and then basically solve function plus c.
Right, so that's right. Find the antiderivative and then solve for the constant. Let's do this one. And
We got the s of o plus the integral from 0.
right, or you can directly use the fundamental theorem of calculus, right? So for my math lab, they gave you a lot of ways to do these problems. The way I can state it, solve this initial value problem, or I could say find the only function that satisfies these requirements. Find the only function that satisfies that requirement. So again, the antiderivative f of x equals the antiderivative of f prime of x dx. By definition, that the antiderivative of the derivative, they should cancel each other out, and you just left with f. I think the constant is 12, right? So sine of 0, the y coordinate with angle 0 is 0. Okay. So that's f of x, and then we'll just use the fact that 12 is f of 0. F of 0 is 0 plus the sine of 0, right, plus a constant. And so that's 0, right? And then the constant is 12. And so the answer is the only function that has both of those properties is 1/5 x to the 5th plus the sine of x plus 12. That's the only one. It's one of the fundamental theorems in differential equations. I know, thrilling. I know. Questions about this? Now, I can phrase this in terms of velocity and position, right? But the question's the same. I could tell some grandiose story about my velocity, and then I tell you my initial position or my position at any time, and then I'm going to ask for my position at some later time. I can do that, right?
Yeah.
Yeah.
So when you give the velocity function.
So I'm going to give you the velocity function. At worst, I give you the velocity function, and then I say my initial position was this. Where was I 30 seconds later?
So you just find the position function.
And then plug in 30, yeah.
So the velocity function would be equivalent to the
Right, the velocity is the derivative of the position. That's right.
And then the initial would be x.
That's right, and it's going to be s of 0 instead of, right, because we usually use
That's
s.
right.
Yeah. Five, you just, listen, just get to it. X squared, x to the third plus 9b to the 45th. Right. So right now my brain is just throwing out tons of these. Okay. How do you do this? So. Oh, we gotta do something like that.
That's 7 or 1.
7.
That's a 7, yeah. So just a bunch of, and let's make this from 0 to 1. So just a bunch of chain rule problems, okay? Substitution problems. I keep calling it a chain rule. A bunch of substitution problems. This is months ago. Yeah. Mhm. 0 to 10. Right now.
The trig function.
Right now.
Right now it's a 9.
2 weeks ago it was like a 1.
2 weeks ago is easy, but it seems like a long time ago. Anybody who's cramming here? Anybody cramming? We're about to do these, but who's going to be cramming before the test? Anybody? 1, thank you. 2.
The trig function.
You're just cramming everything. What is it about trig functions? Yeah, but it's about remembering.
After you do these 4, I'll be good for You think I'm good?
No, I believe you. That's why I'm laughing. I believe you. Okay, so u is x cubed plus 9b, right? So let's do that one. Let's put it in red for the answer. The antiderivative of x squared, x cubed.
That's easy. Doing one of these.
What'd you say?
That's easy one.
This is, oh, no, we're going to do them all. We're going to run through them all.
Oh, okay.
Oh, yeah, we're going to run through them. I'm not just going to do one of these. So.
You know where he's getting tips. He really wants to do can speaking.
Yeah.
Oh, you want to do that one? I see. Du, 3x squared, dx, 1/3 du is x squared dx. This antiderivative becomes the integral 1/3 of u to the 45th du.
Where does the 3 come from when du equals 3?
The derivative of x cubed, you bring the 3 down, subtract 1 from the power.
Right?
3x squared. Bring the 3 down in front, subtract 1 from the power. That's the
Now you
derivative.
can substitute over.
That's right. So this is 1/3. Is that okay? 1/3 times, 1/46. U to the 46 plus a constant. What? Leave it like this? 1/3 times 1/46. What's u? X to the 3rd plus 90 to the 46 plus a constant. You can leave it like this.
better what I have to do calculation.
Yeah, that's just crazy. So
I will definitely make a mistake on that.
good. All right, then the others?
We have to write the plus C, right?
Yeah.
It's wrong otherwise. I want every function that has that property. What'd you say?
It's not defined.
Yeah.
How come we don't see much of the C's and the other problems that we did later on, like tonight?
Oh, because we're looking for numbers.
Right.
Yeah, I want a volume. Give me a number for that, right? I want the length of the curve. Give me a number for that,
And
right?
we pull those constants in the front, right? The ones that
Yeah, that's right. But we're not adding those. That's right.
Okay.
Yeah. These questions. This is asking a different question. I want the collection of all functions that have the property that when you take the derivative of it, you get that. And there are infinitely many of those. Okay. U is tangent, right? U is tangent. 1 over 99. I'm sorry, 1 over 101 tangent to the 101st, right? Did you get that? He's on it. What did you get for this one? No?
I mean, you substitute.
Right, so I guess we should rewrite it. So when I write that,
cross
right?
out the secant squared, and then you should get one.
So the antiderivative of secant squared x tangent to the 100th x dx. We're not going to be intimidated by this. We're not afraid of math symbols, right? I can hide it from you, but not really. This is what I mean. And then of course this just screams, right? This, right? So you let u be tangent du secant squared x dx. This then becomes the antiderivative. Whew. So what happens when I get too excited? The antiderivative of u to the 100 du. Right now we're not even awake when we're doing this part. Okay, so I mean, how many examples do we need? I'm feeling good. I'm feeling an average of, the over-under is 85.5, and I'm taking it over. I'm taking it over. I feel good. I feel good. Questions about this? What did you say? Oh, we're rolling through them.
I know.
You did it faster than I can copy it.
That's my fault. I'm sorry. But I'm trying to send a message. This is where you got to be at the same place. You got to be going this fast pretty soon.
This semester?
You know what? Right. Yes, in days. In days. Yeah. Now, an hour and 45 minutes, 105 minutes, you know, is not that bad. 10 problems, 105 minutes, 10 minutes a problem.
We can't go till 10.
You can't what?
We can't go till
10 o'clock? 3.5. Okay, then I got a new test to write.
Oh, no.
Then I mean that's not a threat. It's just that if you want me to write a 3.5 hour test, then yeah. Oh, okay.
Yeah, we are joking.
Okay, then never mind. Right. So,
Because, I have
but 10 minutes a problem. 10. If I give you 10 minutes to do this,
To do 4.
to do 4 of them, yeah.
If you don't
2.5 minutes.
trig functions, though, you're screwed.
All right. So, but I guess I should remind you.
Yeah, you do get partial credit, right? It's not like
I'm giving partial credit on 80% of the test.
Oh, that's nice.
I'm not giving partial credit for 3 or for 1. 1 and 3. I'm not giving partial credit for 1 or 3.
20 points just for being.
Yeah, I agree. I agree. So I'm giving those points away. So I cannot give partial credit for those. But everything else, we're good.
How long do you?
All right, let's go. So then this one,
So u is 9x to the 8.
u is this, right? The derivative is 72x to the 7th. Who cares that 72 and 4 are not the same? It's the fact that the 7's there, and we can play with all the other numbers, right? So I'm definitely giving one like that, where the numbers are ugly. So, because it doesn't matter. It doesn't matter. So the antiderivative of 4x to the 7th secant squared of 9x to the 8th dx. Let's get it right. U equals 9x to the 8th du is 72x to the 7th. The dx, thank you. The remark is that x to the 7th dx is then 1 over 72 du, dividing both sides by 72. I'm going too quick. But I really want a 4 there, so I'll put a 4 there, and I'll put it in a different color. So 4x to the 7th dx is equal to 4 over 72 du. And now we're ready to substitute, because now we have everything here that is in the integrand. So that this becomes the antiderivative of secant squared u, and then 4x to the 7th dx is 4 over 72 du. And that is the tangent. So 4 over 72 times tangent u plus a constant. And then again, we'll remark that u was 9x to the 8th. 4 over 72, the tangent of 9x to the 8th plus a constant. No?
You can afford.
Oh, no, wait 1 second. Now, you were the one who was doing this in your head. Like when I have a 4x to the 7th and the 72x to the 7th. What do? What do you pull outside of your integral?
Or just 1 over 7, so you can cancel x over 7 with the other one. Oh yeah, you leave 4 bigger, okay.
What to say? You're the expert at this. How are you asking me about? I mean, you're the one who does. You do it in your head. Yeah.
Okay.
I just needed you to calculate. I could see. I could see it in your head. In Spanish too. Spanish too. All right. And what's left? So this one. All right. So I'm gonna leave this one to you. Oh, actually, we should do this one because this is definite.
U is 4x squared.
Right, so u is 4x squared, so the integral from 0 to 1 of 2x e to the 4x squared dx. Right, so I'm definitely going to do one of these. U is 4x squared, du is 8x dx. 1 over 8 du is x dx. I need 2 of those, so 2x dx is 2 over 8 du, that's 1/4, okay? And then when x is 0, u is 4 times 0 squared, which is 0. And when x is 1, u is 4 times 1 squared, which is 4. I'm changing all things here. And so now, this becomes, will this come all the way down here? I don't think so. No, well maybe. This becomes the following. The integral from the integral from 0 to 4 of e to the u,
What about the 1/4?
and then 2x dx is 1/4 du. the whole point of doing substitution. That's the whole point. Is to come down to this point, you're just like, oh, this is trivial.
Remind me again how we went from 0 to 1 to 0 to 1.
Right, so when x is 0, so u and x have a relationship, right? U is 4x squared, right? So when x is 0, u is 4 times 0 squared, which is 0. And when x is 1, u is 4 times 1 squared, which is 4. So x going from 0 to 1 implies u goes from 0 to 4.
Do we need plus c on there?
Absolutely not. Right, because again, we need a
yeah,
number.
this is definitely.
We need a number, that's right. So that's 1 over 4 times e to the u evaluated from 0 to 4. And it's 1 over 4 times e to the 4th minus e to the 0 by the fundamental theorem of calculus. And that's 1 over 4 times e to the 4th minus 1.
Where did the 1 over 4 come from?
2 over 8 is 1 over 4.
Oh, yeah.
Is that all for those?
You might have trouble with my math lab.
Yeah, exactly. I know. I'm sorry, sir.
Could you have done that one without converting the coordinates?
Oh, absolutely. So, I mean, once you find the antiderivative, right, so the antiderivative is, you would have found it to be e to the 4x squared, and then you would have plugged in the 0, the 1 is subtracted.
Okay.
Yeah. But when you plug in the 0 and the when you plug in the 1, the 0, and subtract, you're just getting e to the 4th minus 0.
Okay.
E to the 4th minus e to the 0. So again, it's exactly the same thing. All right, so I may throw in a true-false here. All right, worst case scenario.
What do you mean true false? Like,
A true-false question.
Did you get it right?
I've never had a true false.
You never had a true-false question?
Never. True.
History in the making.
Wow.
So if I say, is true or false, this is equal to 1/4 the integral from 0 to 4 of e to the x dx. Is that true or false? That is true. Because all you do is substitute, and that is what that is. Okay. So I may tack that on. But literally, when you see that question, you say, okay, well, people are just going to be bothered by the fact that they're the same letter. Okay, but it doesn't matter. The letter doesn't matter. Okay, so if you integrate this, then you're going to get, 1/4 e to the 4th minus 1. Okay, so they are equal simply by substituting. Okay. Any questions about substitution? Basic antiderivatives, number 4. Again, I hope these are just gimmies. So you just remember. You can remember. Always write this one first.
This is sine?
That's what?
Sine?
That's
Sine
the inverse
inverse?
sign.
Yeah.
That's right. That's the inverse sign. Right. So you know, yeah, e to the x, all of these. Right? So I'm just going to ask a bunch of them, right? So cosine x minus cosecant, cotangent. Just asking whether you're breathing.
I thought that was cosecant squared.
Sine minus cosine.
Sine.
Oh, plus plus cosecant squared.
Is that right? Yes? That's right. Okay? So that's a bunch of those. So this is number 4. So number 4. Just a bunch of those. question about number 4. So again, we're getting easier as we go back, right? You just remember the formulas. And then state the fundamental theorem of calculus. Alright, so again, it's in the book and it's also in the notes. But number 3, state the fundamental theorem of calculus. I'll take whatever's in the book or whatever I'm about to write or whatever's been written before in previous notes. And so if I say, what's the major theorem that you... I'm sorry, go ahead. So if I say, state the major theorem that unites the integral and the derivative, it's the fundamental theorem of calculus. Okay. Someone in my other class was just like, basically, if you ask a question, how often is it the answer just the fundamental theorem of calculus? I said, 57% of the time, something like that. So if we let A of X, now in the book they have 2 parts, okay? But for me, there's only one part in this one. If you let A of X be that, right? So if you measure the area, the net area under F from A to X, then the remarkable conclusion is that the derivative of the area function is actually the function itself. And so the area function is an antiderivative. So when I say state the fundamental theorem of calculus and explain it in words, then this is sufficient. The crucial thing, again, that Leibniz and Newton connected were these. We had a bunch of people doing areas. We had other people doing derivatives, and now they are forever linked, right? That this problem and this problem had nothing to do with each other for a very long time. Okay?
So that's easy.
Yeah, that's all I'm asking, yeah. So the second part, and I guess I'll put it in parentheses, the second part just says that the integral from A to B of f prime of x dx is just what? F of b minus f of a. Right. That's the second part. But I only need the first part because, again, the second part follows from the first part.
And the other one was where you could switch it by putting a negative in the front, right?
But that's not part of the theorem.
Right.
That's a definition. I don't know what to say about that. And then that's 3, and then 2. Oh, left and right. Right hand point method, left hand point method. Do we need to do one of those? So we're saying something like, pick a function. X cubed, so f of x equal to x cubed on the interval 0 to what?
4.
0 to 4. How many rectangles? 4. Method? Right. See? Make your own damn test questions.
I mean, the middle two, right?
No, I'm going to pick one. I'm going to roll some dice or something and just say, okay, it's the left. It's the midpoint. It's the random, right?
The random.
Yeah. So, yeah. Someone just raises their hand when you're on that problem, and I say left. Someone else raises their hand. That will be just a brutal thing to grade, right? Okay. 0 to 4. 0 to 4. 4. So each one is of length 1. B minus A over n. Right, so 4 minus 0, 4. Each one's of length 1. That means this is 1, that's 2, that's 3. Right endpoint method. This is delta x, right? So right endpoint method, 1 times f of
3? What are you talking about? Look at something from the right.
We are doing the right endpoint method. The width is 1. What's the height? Thank you. F of 1 plus 1 times f of 2 plus 1 times f of 3 plus 1 times f of 4. And that equals 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. I'll take your word for it. I don't think it's 66.
No, 64. Sorry.
This is 64 alone.
No, but to find the area.
The actual area? Oh, that may be right. I think it's 1/4 x to the 4th. Yeah, that's right. The actual area is 64. Yeah. But you can see this is an over approximation. Okay. The right endpoint method on an increasing function is an over approximation. True or false?
True.
That's true. Right. The right endpoint method on an increasing function. All right. So if I say draw a function representing that, that shouldn't be a problem. Questions about this? This would be funky, but it doesn't matter. You're just plugging in points. Okay. Say it again. Oh, you can, yeah. So the left, we'll put it in red. So the left endpoint method. 1 times f of 0 plus 1 times f of 1 plus 1 times f of 2 plus 1 times f of 3. A useless 0 plus 1 squared plus 2 squared plus 3 squared. What is that?
Cube.
This is 36?
No,
I
mine
thought it
was
was
4,
cube.
13, 14.
Okay.
It's cubed.
Yeah.
Oh, it's cute. Thank you.
Oh, yeah.
Yeah, I didn't lose my mind.
So you do 35, 36.
I'm sorry, say it again?
36.
No, what you were saying. Nick, this is ridiculous? Okay. Why is it ridiculous? What's ridiculous?
I don't know. Seems like it should be
Oh, so yeah, it seems like it should be more difficult, but there you're going to be with your 89. I'm going to be hard on you. It should be more difficult. I want a 99. That's right. 36.
Clearly, the answer is no.
I mean, listen, it's really, really difficult to cheat on the math exam.
It was difficult when you had to write all that in Riemann sums.
Right, exactly. I mean, it's just difficult. So, yeah. So, sit wherever you like.
Yeah.
When I was a TA in graduate school, I think I told you this, right? So, I was they had all sorts of cheating schemes, right? I told this story before to my Calc 1 class. And so, as you know, it was my first year in graduate school. It was 1990 something. And I'm in there, and it's my first year, so people just say, okay, you got to watch out for this. And they have something called the Singapore Triangle. And so everyone's sitting, by the way, I've had everyone's attention way more than in the last 2 hours. Let me just say that. Okay, so the Singapore Triangle, you know, there's like a sloping auditorium. And so one person knows the answers, and then there's a triangle that builds from that person. And so there are 2 people sitting behind them looking down, then there are 3 people sitting behind those 2 people looking down, and they all cheat back. Hopefully it's not a bad game of telephone, right? So that the first person writes 12, and it gets back to the last row, and it's 172, right? Hopefully that doesn't happen. Well, hopefully it does. What am I saying? Okay, so...
What was that triangle that you go
The
down?
Singapore Triangle? Or,
Where you go
I'm
down,
sorry.
Like 1, and then it's 0 in the middle, then 1's on the side, and then you keep going.
That's Pascal's triangle.
Pascal's
Yeah, that's Pascal's
You use
triangle.
that for
Right.
the derivatives, right?
Right, you can. So the derivatives of the product rule, right? So if you want to know the fourth derivative of f times g, you can figure out what that is using Pascal's triangle. That's right.
So
And then, I'm sorry, please.
in the left endpoint as opposed to the right endpoint, you just ignore 4 and use 0.
Right.
Use the first one.
You use the leftmost endpoint in each subinterval. So in here, these are 4 subintervals. Here's 1, 2, 3, 4. And in each subinterval, you have to make the choice of what you're going to plug into F. And the left endpoint in this first subinterval is what you pick, 0. And in this subinterval, you pick 1. In this subinterval, you pick 2. In this subinterval, you pick 3, as opposed to the right endpoint where you pick 1, 2, 3, and 4 in each subinterval.
And if you did the midpoint, you'd use all 0 through 4, and then it would be half, right?
For the midpoint, it would be 1 times 1 f of 1/2, f of 1.5, f of 2.5, and then f of 3.5.
Oh, okay, right. You take the average of the points.
It's the midpoint, yeah. And then define the integral. And so then finally, we're defining the integral, number 1. And you can use what's in the book if you like. And so again, we need f continuous on a to b. And I won't put the 1 there. And that's the requirement. Does f have to be continuous to create an area under it? Does f have to be continuous? Must it be continuous? Are you telling me you can't find the area under this? Can you find the area under this one? A to B? Can you find the area under that curve?
I mean, it's possible.
Yeah, you can. So f does not have to be continuous in order to define the integral. Okay. Yeah, that's right. That's right. So you can have multiple breaks in order to find the area, right? So the technical term is that you just need to be continuous almost everywhere, okay? All right, so you break the interval A to B into n pieces, right? Break the A to B into n equal pieces. Again, we agreed that it has to be equal. Do they have to be equal?
No.
No. In equal pieces of length delta x. 2, and each piece pick a place x where the height is to be taken. And then form the Riemann sum. So form the sum of the rectangles. And then you let the number of rectangles tend to infinity. And that is the interval from A to B. Now the book talks about partitions and all of this other stuff, okay, which is perfectly fine. Right? But that's good. Well, and with that, I'm here for another at least 15 to 30 minutes to take whatever questions you have. Again, on Tuesday, I will be in the AEC from 2 until the start of this class. Please. Why am I not there? Oh, I just decided to be there on Thursday. I have the free time, so I just said I'll be there on Thursday. There's nothing keeping me there, but I'm there. Right. The place needs as many people as possible. right? Particularly, they don't have enough tutors for like advanced math. So people in like real analysis and like differential equations don't have tutors there that can help them.
Yeah, I don't think they have tutors for the iTech classes either, because like
Right.
digital.
iTech's bad, especially with programming.
Oh yeah, yeah.
Is that enough learning?
I don't know that much about tutoring like iTech. How do you do that? So what are they looking for? Like syntax errors, or like syntax error issues been solved, right, with these editors, hasn't it? Like, so that if you like, you don't like missing a semicolon, you can find.
Well, yeah. Well, if you're using the IDE is kind of easy, like something like that, something small like that, like a semicolon. But sometimes it'll give you an error, and what it tells you isn't. It doesn't make it clear what your error is.
Oh, okay. And then someone who's really good at it can just, who's a good tutor,
can say,
oh,
they
that's
can look at it
clearly.
and go,
Oh, okay, so you don't have that yet over there. In the
well, there are, but there's
Spotty.
not. Yeah, it's very
Okay.
spotty.
Okay.
Do they hire tutors, or is it all volunteer?
Well, you know, I'm pushing for them to put students over there. As you can understand, but that's kind of new. As you can understand, maybe back in the day when we were a new school, we were hesitant to put in students who weren't even seniors yet. But now, I think they're accepting. Yeah, I agree with that. I agree with that completely.
I've had any time in my life I would totally do it.
Yeah. Well, the money's good. I think it's like, I mean, for just being a tutor, $10 to $11 an hour.
Said that he charged like $50 when he was.
Oh, so do I. Yeah, it's like, yeah.
So you only get 2 days, or
Now, name another day.
it doesn't really matter.
Yeah, I mean, I'm there on Tuesdays and Thursdays and by appointment.
Also Thursdays?
Yeah. Yeah, so I can be there this Thursday. Just let me know when, because I'm headed out of town this Thursday. So I would prefer directly at 2 if possible. So we can work on an hour.